In general, we can think of a field as a value, be that a vector or a scalar, that is assigned to every point in space. An example you've already encountered is actually Coulomb's law, which maps out or associates a vector value equal to a force a charged particle experiences at every point in space. For example, shown on the screen is a positive charge distribution, and in its proximity we now place a positive test charge. This test charge will experience a radial force due to Coulomb's law. I can now map out the force field around our charge distribution by moving around the test charge and mapping the force that it experiences. So at every point in space, I can calculate the force experienced by the test charge. This means at every point in space there's a vector quantity that is the force that the test charge experiences in the vicinity of our original charge distribution. This just defines what is known as a force field, and it is basically given by Coulomb's law. Depending on the distance away from the charge distribution and the radial direction, I can map out a force for every point in space on this screen. We can define a quantity that's independent of the amount of charge carried by the test charge by simply dividing by the charge that was carried by the test charge. This leaves an expression that we define as the electric field. Now, electric field is again a vector field. It maps out a vector quantity for every point in space around a charge distribution. It is a useful quantity because if our test charge is so small that it does not affect our original charge distribution, we can map out the electric field around our original charge distribution and then use that to calculate the force that any test charge will experience in the vicinity by mapping out simply the electric field.